This is part 4 in a series of videos in which I'm attempting to repair and restore this machine. If you haven't seen the previous videos, this is a Cromemco System 3. It's a very old system. It was designed back in the very late 1970s, and it's built like a tank, but fundamentally inside it's very simple. It's got Z80 or 68,000 based cards, and like any S100 system, it has various add-on cards that provide functionalities such as floppy drive controllers, in-out memory, that sort of thing. And it adheres to the S100 bus, so it's very familiar to anyone that's familiar with that type of computer. So in the previous videos I've gone through the chassis, I've cleaned it up, gone through the power supplies, made a few minor repairs, got it working. So the next thing to do is start looking at the cards. So we'll start with the processor card. In this machine it's a Z80 based card, but you can get dual cards for this, and there are various options running Z80 and the 68,000, but this one just has the single Z80 processor. And the way this machine works is very simple. When you boot up the machine, the processor jumps to a predefined address, and at that address it hopes to find some ROM, and it will use that ROM to boot into the system. So it does have a boot ROM and monitor program. And that normally is responsible for loading the operating system from floppy disk. Now, if you're familiar with this card, you'll probably already realise which particular controller it has fitted. So the switches over here on the right determine the address that the processor jumps to when it's reset, and this particular one is set to jump to an address of C1000. So again, we'll come back to the meaning of that later on. But the question with a system like this is always where to start testing it, and of course there's as many answers as there are systems, and I like to try and make these videos interesting, so I'll do something different each time. There is no right or wrong way to do this. The most important thing to remember is it's supposed to be fun and experiment. Once you get the fundamentals of systems like this properly understood, then they're all just really a variation on a theme. So exactly how you then go about testing various machines is up to you, and you can sort of mix and match and choose your favourite approach. I just like to experiment and try different things, but the main thing is to try to work in a logical manner. So what I'm going to do with this machine, because it has what is essentially a standalone processor that's looking to boot from external code, that actually gives us quite a nice method of testing it. So in order to test this, what I'm going to do is actually use the Jade Bus Probe. So if you're not familiar with the Jade Bus Probe, that's one of these. So I have a number of these. Whether these are useful for other processors or even for an S100 depends on what you're trying to test. It doesn't really do very much, and in its standard form I would say it has limited usefulness. Where it really becomes useful is if you're doing specific types of testing, and in particular if you've got a faulty machine, then how you use this is entirely up to you. It's quite useful for single stepping through code if you're developing something. The problem is, of course, that if the system isn't working, you can't single step through it, and so the usefulness of this card is questionable. But where it really comes into its own in that situation is if you're familiar with the S100 bus, then you very quickly will see any errors on the bus, because all these LEDs are really doing is showing you the current status of the individual pins on the backplane. Where it becomes a bit more useful is with these switches here that allow you to single step and display particular bus cycles. So if you're trying to look at memory cycles, for example, then you can select the appropriate switch and then as you single step through the system, through the code, then you can look at that particular type of bus cycle, and it does become very useful there. Now, I did a quick video on this card and some options in building it, and I got a comment about whether you could use something like an FPGA and e-paper, for example. And yes, you could. If you're not familiar with electronic ink, or e-paper as it's called, this is an example of e-paper. This is from a project I did about 6-7 years ago now, and you can see this has an image on it, but I haven't powered this up for probably 6 years now. This was just an experiment to see how good e-paper was and how to drive it, and it ended up being for a fairly big project. And this is just one of the test cards I ended up being left with. But I left it in a box just really to see how long the image would last. And as I said, that was at least 6 years ago, and as you can see, the image is still very clear. But there's no battery on this, there's no battery backup, there's nothing really to retain the image other than the display itself. You could unplug this from the card and the image would stay there. But as you can see, the image is retained for years and doesn't need power. So yes, you could make an extremely low power version of something like a bus probe using this. The problem with e-paper, electronic ink, is it's extremely slow. It's a very slow display technology. And one of the things you find with something like the bus probe is if you do use it a great deal for specific types of machines, you become familiar with the pattern of LEDs, and you can then see if it doesn't look quite right. You get the same thing with Altair 8800s, for example, where when you're loading code into them, you become familiar with the LED displays on the front. Even though they're not really changing, some will be dim, some will be bright, and that pattern becomes fairly familiar. And that's where this is fairly useful. Now, you wouldn't get that with something like electronic e-paper displays, because they're too slow, and because you're then updating them and they're digital, you kind of lose this dynamic feedback that you get from a card like this. Okay, so that said, the first thing I'm going to do is look at testing the processor card. And the way I'm going to go about this, I've already been through this and done some basic testing, looking for shorts on the bus, that sort of thing. It has got some tantalum caps on here, so I was testing those. Every IC is in a socket, so I have slightly lifted and reinserted all the ICs just to clean up the pins. Some were quite dirty, and I've been through, checked for any poor connections, any work that's been done on it, and it actually looks to be in very good condition. I couldn't find any issues. I popped out the Z80 and I tested that in another board that I've got on another machine, and that works fine. So it appears that this card, at least on the face of it, should function correctly. But what we can do now is run it through a simple test. And as I said, because of the nature of this machine, there's a very straightforward test we can run to see if this card is working at all. So first thing I'll do is get this plugged in. Okay, I've got the Z80 card plugged back in. Doesn't really matter where it goes, but I'm putting the cards back in the same slots they were in when I got the machine. And the next thing I want to do is plug in the bus probe. I'm going to plug this into the end slot so it's out of the way, and also so that I can properly see the LEDs with the rack pushed most of the way back in. So what I'm going to do is just push the rack in a little way, and then we can insert the bus probe. I'll move the camera a bit so you can see the display on the bus probe itself in a minute. But this just plugs in like any other card on the S100 system. So I'll move the camera now so you can see the LEDs on the Jade probe. Okay, so that's plugged in. Before we start, what I'm going to do is just move one of the jumpers on the bus probe. This is capable of displaying a 24-bit address bus, but this particular machine only has 16 bits, and to avoid any confusion with the upper 8 bits, I'll disable this block of 8 bits, and there's a jumper specifically for doing that. Okay, so these top 8 address bits will now be inactive. So what we can do now is power this up. Now what we have at the moment is a situation where we have the Z80 on the backplane, and it's going to jump to an address of C1000 because of the setting of these switches down here. That's assuming this card works at all. And what that's going to cause to happen is the Z80 is going to try and obtain an instruction from a ROM at that address. But of course there is no ROM on the backplane. So what we're going to do, because we've got the bus probe attached, it will actually load up the data line slightly, and that will pull them all low. So what we're going to end up with is the data returned to the Z80 will always be all zeros. And if you're familiar with the Z80 instruction set, you'll know that that will give you a NOP instruction. When the Z80 executes a NOP instruction, it will do nothing other than increment the address pointer, the instruction pointer within the processor, and then it will try to obtain the next instruction, which again will be a NOP. So what it will effectively do is, just starting at C1000, it will just incrementally work its way through the address bus values, counting up by 1 each time, and then it will wrap around and start again. It will just keep doing that as long as it's powered up, assuming that the board is actually running. And we should see that, it'll be very quick of course, and we should see that by the upper address LEDs flickering. They'll all be switching of course in theory, but we'll only see it on the upper address lines because effectively they're slowed down, and we should see the flickering on them. So it's a good way to test to see if there's any activity on the bus at all. Be careful when you're doing this sort of thing. Make sure you're not going to do any damage by running it with certain cards removed, but in general with an S100 system you shouldn't do any damage by running it like this. Okay, so I'll get this powered up, and I don't know how well this comes out on camera, but indeed the upper address lines are flickering. So what I'll do now is power the machine off, and you can see it's going to take a while for some of the supply voltages to drop, simply because it's got huge capacitors on those rails. These LEDs here, these three, are monitoring the 3 power rails, but they're not window detectors or anything fancy like that. They just come on power through a resistor from the rail, so it's not telling you if the voltage is correct, it's just telling you there is power there. And again, as I said, it's a very simple card. It doesn't do a great deal. One thing that we can look at are the clock lines. So if I power this back up, we can see that the 2 clock lines are both illuminated, and assuming that your bus probe is working, then that means that there are clock signals present on the backplane, because these are run through an active part of this board where it requires the circuits driving these LEDs to be constantly refreshed, otherwise the LEDs will go out. So if the clock lines are static and stuck either high or low, then these 2 LEDs should go out. And we can simulate that. If we pop out the IC that's driving the clock lines, so I'll pop out the IC that's driving the clock line. I'll now power it back up, and we can see there's no activity on the system, and the 2 clock LEDs are out. So again, it gives us some confirmation there's at least something going on, and we're getting the expected results on the address lines. Okay, so I'll turn it back off and put that IC back in. So although we're getting some basic indication as to what's going on, we're not getting a lot of particularly useful information, but we are getting some basics as to what the system is doing. Now we could break out a logic analyzer, a scope, and start doing some more detailed fault finding. But what you'll notice here is that on this particular Jade bus we've got a couple of extra switches. There's one at the top and one at the bottom. Sorry, you can't see that. I'll just tilt this down a bit further. and there's one down here. So I've modified this bus probe, and what these two switches do is allow me to put the S100 bus into a single step mode. So if I turn the top switch on, the bottom switch then becomes a single step switch. To make it a bit clearer what's going on here, I've actually reproduced the modification on this board on a breadboard. So it's nothing more than this circuit. So it's a 74 LS38 and a 7474, and then we've got a bus connector here, so I can easily make connections to the backplane, and I can plug this into whichever slot on the backplane I want, and then I have the same two switches here to enable me to switch in and out of single step mode and then to actually single step the system. And that makes it far easier to see what is actually going on, and we can actually even then start to look at the values being obtained from any ROM, and of course what address that data was obtained from. So I'll get this plugged into the machine. All I'm going to do is insert this into one of the backplane connectors, doesn't matter which one, and then we can single step the system. Okay, I've got this plugged into the backplane. I'll power the machine back up, and I've got the circuit set so it's allowing the system to free run as it normally would, and you can see we're getting the same results here. So what I'll do now is I'll switch it into single step mode. You can see this is now stopped, and what this switch should now do is allow us to single step the processor. And as you can see, each time I hit the switch, it's stepping through to the next phase. Now the way this circuit's configured, and again, you can do this sort of thing however you want, and it's one of the methods I use a great deal for different types of equipment. You've got to be fairly careful on some equipment, whether multi-master buses and that sort of thing, you can't really do this. But for simple systems like this, it's a very good technique for finding out exactly what's going on. And it's kind of a bit like using a logic analyzer. You can put the machine into a certain state, step through and see exactly what is going on, and that's where the bus probe becomes quite useful. You can see at a glance what's going on, and depending on the mode that you've got selected, you can look through memory reads and writes and that sort of thing to see exactly where any faults might lie. So if you are interested in how this circuit works, it's extremely simple. On the S100 bus we have this X-Ready, this external ready signal, and it's used to essentially halt the system. Now of course it does rely on the card that you're using to implement that particular signal, but most do, and when you assert it, it puts the processor into a halt mode, so it just holds the processor and stops it running. And that's what this circuit does. Every time we hit the toggle switch, there's a latch and a flip-flop, and it latches the X-Ready line into a state that is essentially allowing the system to run, and that's when we've got it into its single step mode. And because the system's running, what happens from that point on is the system will run, and then the second input to this circuit is coming from the P-Sync line, and this line is asserted at the start of any particular bus cycle. So the way the system operates, you hit the toggle switch, the system is latched into operation. Doesn't matter if you're still holding the toggle switch, the way the circuit's arranged is it's not resettable until you release the switch. So the latch is set, it enables the system to run, and then when the P-Sync starts at the beginning of the next bus cycle, or when the P-Sync's asserted at the beginning of the next bus cycle, the latch is reset and it reasserts X-Ready, and that halts the system again. So in other words, the latch is used to enable the system to run, and then the latch is reset using the P-Sync signal, which halts it again, and the switch is just used to kind of clear that latch to enable the system to run through its next cycle. So the advantage of a circuit like this is it means you can hook it up to any signal you want, and you can cause the system to run up to whichever part of the bus cycle you're interested in. So it's quite a useful tool, and especially used in conjunction with the bus probe, which is why I added it to the bus probe and modified the bus probe like this. It's quite a useful tool to use to enable you to step through and examine various parts of the operation of the system. The bus probe itself, as I said, if it's just free running, it's interesting to look at but not particularly useful. But when used like this and used in conjunction with other methods, it is quite a useful display tool. It's a bit like a logic analyzer. A logic analyzer in its own right is not particularly useful. It's only useful depending on the data that you capture with it. And the same is true of the bus probe. You need to use it as a tool. It's not going to give you an answer every time as to exactly what's going on, but it does give you a nice indication as to what the bus is doing. Okay, so I'm going to do a bit more testing on this card, and assuming I don't find any issues, then what I'm going to do is put in the memory card, and assuming I don't find any issues with that, then we can move on and put the ROM card in. We'll look at the ROM. The ROM card itself is quite interesting. It's not just a ROM card, it's a floppy drive controller, serial in-out, and the boot ROM, so it's quite an interesting card. But we'll get the processor and the RAM card working first. The source of testing I'm going to be doing is just putting a scope on the address lines, checking the various inputs and outputs of the processor card to make sure that it's working the way it's supposed to. And that way we can be fairly confident that when we put the next card in, we're not going to get any issues. Okay, so I've spent some time going through the first three cards. Couldn't find any faults with the Z80 card. Couldn't find any faults with the RAM card. This is a 64K RAM card, but I did find an issue with the floppy drive card. So if anyone that's interested, this is the 4FDC card. So this is quite a popular card. I've got quite a few of these. I actually use them for testing other types of S100 machines. They've got quite a nice architecture. They're quite useful for this sort of thing. This particular one has PDOS 1.3. So the way this card works is that it's a combined floppy drive controller, boot ROM, monitor and serial card, and so the output from this is what you'd normally hook up to something like a dumb terminal. I haven't got the cables plugged in at the moment. I'm not that far through the testing, but I couldn't get this to work, and I'll show you how I determined it wasn't working in a minute. And it turned out that it was a failed ROM. So I'll just pop the card out. So we'll just pop this card out and I'll show you what the issue was. So, as I say, it's quite a nice card. It's fairly limited in its performance and the things it can do, but in terms of the functionality it provides in a system like this, it's quite interesting. But the ROM had failed, so I've blown a new ROM. As I say, I do have a number of these cards, so I've long since taken the images from these, and I put the newest one that I have in here. So PDOS is really the what amounts to a BIOS for this machine. Very simple, and its function really is to do some basic boot up for the machine, and then to try and load an operating system from a floppy drive. And the floppy drive plugs into the connector at the top, and it also provides serial in-out, and for the PDOS system that provides the interface to a dumb terminal, so or some other control system. So it's quite nice, but as I said, the ROM had failed, and it is a multi-bus, multi-supply ROM, so just be aware of that. So 2708 is what I fitted, and as I say, I'll put the latest version of PDOS I have, and what we can now do is plug this in and see if the system will function. What I was getting initially was no activity at all, so that was caused by the ROM not working. What we'll do, I'll push this card back in so you can see the display on the Jade Bus. I've still got this circuit plugged in, so I'll use these switches to try and single step. Remember that the Z80 card is set to jump to an address of C1000, and so that's 1100, zeros all the way down, and it should start trying to execute code from there. So assuming the system is working, then that's what we should see. So when we first boot this up, we should see address bits 14 and 15 illuminated, and that shows that we've reset to the correct reset vector, and then we should start seeing the address incrementing, starting at address 0, and then of course it will probably jump somewhere. But we can do that step by step because we've got this circuit plugged in, or normally we could use the switches on the Jade Bus. Okay, so I'll get the machine powered up. Okay, so it's powered up in a random form because we have the single step mode turned on, so it hasn't been able to complete the first bus cycle. But if I get it to complete the first bus cycle, then we can see that it has indeed jumped to the correct start vector. And what it will now do is start trying to load data from the ROM. I should say this single stepping is not instruction single stepping, it is machine cycle stepping. So that's one thing to bear in mind if you're doing it like this. You need to make sure you understand which particular part of the bus cycle you're in when you're looking at the data or the address. But as we start stepping through, we should start seeing data coming through onto the data bus, and what we can then do is compare the values we're seeing with the values we expect to see at these addresses in the PDOS ROM. Because we have a copy of the PDOS ROM, we can of course just look at the addresses and see what should be at address, in this case address 1. You can ignore these two, of course. This is just the base address for the ROM itself, and so this will now be at address 1 in the ROM itself, and we can see should it have this value. And I've been through about the first 30 or 40 addresses and they're correct, so it is successfully reading the correct values from the ROM, and because it's reading the correct values and then jumping to the correct addresses, we can be fairly confident that the system is working to a fairly large extent, because it means that the processor card is able to obtain data values from the ROM. It's able to write the values when it needs to into the RAM, and then it's able to jump to different addresses, and we can then trace through the startup operation of the system. Okay, you can only go so far doing this, but again, it's a useful tool for this type of basic testing, but it obviously has its limitations. And so what I will be doing now is just running this through its paces, doing a bit more testing. I can switch it into normal run mode, and notice some LEDs are dim, some are bright, and it just shows there is activity on the various buses. And what I can do now is use a scope or a logic analyzer to examine what's going on here, and assuming it looks correct, we can try hooking up a dumb terminal and see if we're getting anything coming in and out of the serial port of the floppy drive controller card. And if we are, we can then start trying to get the system to boot up, and the next step will be to hook up the floppy drive. I need to go through the floppy drive first and make sure it's working, carry out a few repairs. But we are getting closer, and as I say, how you go about this sort of thing is entirely up to you. Whatever method takes your fancy, really. I tend to go through it in a fairly methodical and logical fashion. It just avoids doing any further damage if anything isn't working properly, and ultimately I find it quite an interesting way of carrying out these repairs. Any questions or comments, please let me know.